Good morning from our side, from the Jülich Supercomputing Center. Let me introduce my co-director, Professor Kristel Michielsen. She is also the head of the quantum computing and of a new infrastructure that we have brought together with computers, with quantum computers, where the D-Wave machine is our flagship machine called JUNIQ. And I'm the director, and I'm mainly responsible for the HPC part of the center, but I'm also quantum physicist. So just to give you an idea where we are located, this is at the nexus of Belgium, the Netherlands, and Germany in a small town that was founded by the Romans, and at this time it was called Iuliacum, now it's called Jülich today. We have about 7,500 people from 114 countries. And in the Supercomputing Center, we have about 356 technicians and scientists from 41 countries. So we are quite a multi-country, multinational center in Jülich. Our mission primarily is to promote supercomputing. And one of the stages of supercomputing, it goes all with our numbering system, 10 to the 9, it's giga, 10 to the 12 tera, 10 to the 15 peta, and 10 to the 18 floating point operations per second. We call exa computing. You might know what comes next. It's zeta, but what comes after zeta? Iota? Rona? Quetta. Okay, that's where computing will go, and also where D-Wave will go in the future. So there is a lot of activities there. It's high-end simulation. It's large-scale AI. It's what we call the foundational models, the large language models, the large multimodal models. All of this is on our plans and activity schedule. And of course, we are researching new technologies, future technologies, like quantum computing, quantum annealing, neuromorphic computing, and I mentioned it before, the digital cryocomputing. We believe that computing will undergo a transition towards a direction where the energy per floating point operation has to be brought down by a huge factor. And here, we are very close to what quantum computing is, for instance, with the quantum annealing. We need cryostats. We need to go to very low temperatures to achieve this goal. But my prediction, in 10, 15 years, this will be the direction of computing. Now, we also do many other things. We federate computing in Germany, in Europe, worldwide. You might have heard about the SKA, which is the astronomy project to go towards the edges of the universe. We have effective support structures, and we educate new scientists in HPC, in AI, and in quantum computing. So that's where we head now for. We are at the end stages of the implementation of the exascale supercomputer Jupiter. Jupiter stands for about 1.35 exaflop raw power and 1 exaflop of Lindbergh power, but it stands for much more. It will provide more than 40 exaflop AI compute at 8-bit. So this machine has a dual role. It's a simulation machine, and it's also a computing machine. The main point here is that it is a machine that we call a modular supercomputer. In a modular supercomputer, you join different elements. You have a sort of administrative system. These are the classical cluster computers. But you have also some things that we have very naturally called a booster. This is a module that uses dominantly GPUs and the most modern GPUs. So the cluster and the booster are brought together. And of course, you can, when you have achieved such a software environment, an operating system environment, where you can include all of this also in a user program, then you can include a quantum computer, a quantum annealer. And that's the reason why we call in the future the D-Wave systems that we acquire now, that we call it a module in our supercomputer environment. It's not a module that is less than the Jupiter. It's of its own, let's say, virtue and its own reasoning why we have it, but we bring them both together and we want to make more out of that. And you heard it before, one very important activity will be to boost the performance of the training process of large foundation models by means of the quantum computer. I think this is very close to us now. Now, our computing strategy has paid off in several projects. One of those is a language model we call OpenGPTX. It's one of the first open models in the sense that all the links that go into the training are controlled and controllable. That's an important issue for the future, for the ethics of computing, because we have to know by which type of material we are training our models so that we give them to our children and to all other people in this world. And this OpenGPTX is now in a stage to be provided. It's called Token. It will, on Jupiter, be trained as a model with several hundred billion parameters. So this is where we head for AI. Another AI activity is weather forecast, climate prediction, where we are quite advanced and can compete with any other of those most successful type of endeavors in doing meteorology with these AI methods. If we now, I could go on. I just had a review and I had to present about 20 of those projects, but I would like to stop here with the application of Jupiter and of our activities in the field of quantum simulation and quantum computing. On the one hand, doing quantum simulations, on the other hand, to emulate the basic operation of quantum computers. And all of this goes down, let's say, to the year 2010 or so, when we first conceived our goal towards exascale. At this time, maybe about 40, 42 qubits could be simulated on the machines. Meanwhile, we are heading for 50 qubits. This is quite something. So having 50 qubits on a classical computer requires an exascale machine with its memory. And this is where I would want to hand over to Kristel. Kristel, please take over and explain these people what quantum computing is. Thank you.
Thank you. So good morning. Yes, why are we making these simulations of quantum computers? First of all, we want to know how these systems operate. And this also holds for the D-Wave quantum computer. So we use this type of emulations on our classical computers in order to understand the operation of the system. A second goal is to look into quantum algorithms and to study the how these quantum algorithms by itself perform, but also how they perform if you put them on a noisy quantum computer or if you do some annealing, and where you can make combinations, where you can make improvements. So in Jülich, we have, at the Jülich Supercomputing Center, developed our own quantum computing strategy. And the first pillar is the modeling and emulation, exactly for the reasons I have given you. And with the software product, you have seen the Jülich Universal Quantum Computer Simulator. We also have been participating in the quantum supremacy project of Google, in which we benchmarked the Sycamore processor. Now, the second pillar in our strategy is to install, operate, and provision quantum computing systems. And the first system we provided our users access to was a quantum annealer of D-Wave, which we are hosting since 2022. Then, in order to come to practical quantum computing, our vision at the Jülich Supercomputing Center is already for quite some time that one has to integrate these high-performance computing systems and quantum computing systems. One has to combine the best of both worlds in order to make some progress. And then last but not least, we know that users are very important. Not only scientific users, also all kinds of industrial users for their applications. So, and for this purpose, we have created a quantum computer user facility called JUNIQ, the Jülich Unified Infrastructure for Quantum Computing. In this user infrastructure, we do not only provide the users access to the system, but we also provide them with training. We provide summer schools, spring schools, and so on. And together with our customers, we work on applications. This can be a scientific application, but this can also be in an industrial project where we work together with our industrial customer to come to some type of application. So here you see a picture of the building of the quantum computer user facility, and actually that's the building that hosts the D-Wave quantum annealer since 2022. In this building, we have 2 machine rooms. At the moment, one is occupied by a D-Wave Advantage system, which will, in the near future, will be upgraded to the Advantage 2 system. And then we will have a second system. So we will have one that we host and which we do experiments with. That's the one we purchased. But for a long time, we're also hosting the European system for D-Wave. So there will be a second one. And it's very probable that we will host both systems in this building. Now the history, as Thomas already was saying, his first contact with D-Wave was in November 2007 at a supercomputing conference in Reno. So there D-Wave had a small booth, and they were presenting some prototype applications on one of their first chips. It only had 28 qubits, but nevertheless they were making a live demo. And Thomas was so enthusiastic about it that they had a lot of discussions. And you see now at the Jülich Supercomputing Center, we are hosting and operating one of their systems. So in October 2019, we had our festivity, namely for the signature of a usage contract with D-Wave. That was the first system that we were hosting, the Advantage system, an entirely European system, which was also very important for the European companies because they want to compute under European legislation. And then finally, in January 2022, we had the deployment of our system. I must say this was a major accomplishment because in between ordering the machine and installing and calibrating the machine, we had COVID. So it finally took us all a little bit longer, but we finally managed. So I want to give you now some applications from a scientific point of view. And you know, in quantum computing, there are 3 major application fields. You have optimization, you have quantum machine learning, and then you also have quantum simulation. So this first project is a project which was done in collaboration with Boeing. And the reason is it's an optimization problem from the airline industry. The task is to assign aircrafts to flights, thereby minimizing the overall cost, respecting operational constraints. It's an optimization problem with a huge number of constraints. So each airline has different types of airplanes. They have different routes. They are carrying persons. They are carrying goods. they have to take into account with the working times of their personnel. So every day, they have to solve huge optimization problems. It is clear that a quantum computer, also not a quantum D-wave annealer, can solve such big optimization problems. So one always has to simplify the problem, and one also has to make it smaller. So we made it smaller to a problem with 40 qubits. And now you can ask why 40, because D-wave has many more. Yes, but we could simulate 40 qubits on our HPC system. So then we could make a comparison between quantum annealing and the optimization algorithms, the quantum approximate optimization algorithm, which one can be running on a gate-based quantum computer. So we wanted to do some cross-platform benchmarking and see what quantum annealing can do compared to the gate-based systems. So therefore, we have been running this Quaoa on our supercomputer. And on the right there, you see a figure with the outcome. You see the success probability as a function of the number of qubits. And Quaoa are the green dots, or the green square. So what did we notice? We noticed that if we have this quantum algorithm, which was considered to be a good one for a gate-based quantum computer, on an emulated quantum computer, so an ideal one without any errors, there is no influence from temperature, we noticed that when this quantum computer becomes bigger and bigger, our success rate is decreasing. So we noticed even an exponential decrease. And then we thought, oh, in that case, this quantum algorithm will not be a good one for the gate-based quantum computer, because if it becomes bigger, it becomes useless. So then we tried several improvements, but although we succeeded improving a lot, we also have been looking what D-Wave was doing for such type of problems. And not only the ones with 40 qubits, but also bigger ones. And there we immediately saw, without making any extra efforts, that we already had a success rate of 70%. And we know that when the machine becomes bigger, when the coherence becomes better, when the connectivity between the qubits becomes higher, this can only improve. So a second project which I want to highlight here is one related to quantum machine learning. One algorithm in machine learning is the support vector machine. And we have put this onto a quantum annealer for different purposes. And one purpose was classification of images. So what you see here is on the left side a small picture of the city of Toulouse, in which there are 3 classes. So one blue, which is water. Then we have in orange the buildings, and then green we have pervious surfaces. So the left picture is the ground truth, and then on the right you already see what a classical support vector machine was giving as an outcome. As I said, we have been putting it on the quantum annealer for binary classification, but of course one also wants to do multi-class classification. So we kept on extending our algorithms. And then now on the right there, you can see what the outcome is with a D-Wave quantum annealer. Now, the good news is that we see a result that is comparable to what we know from classical machine learning, but it scales more efficiently with a number of training samples. So the D-Wave quantum annealer can play here some important role. Now, all of you know that this quantum machine learning is one step towards AI. So quantum annealing will also play a role in what is now the new field called quantum artificial intelligence. A third project from quantum simulation, as I said, this is the third field in which quantum computing is believed to bring some advantages. And here this is a recent result, namely about simulating the reconfiguration of quantum domain, the dynamics of the quantum domain reconfiguration in particular two-dimensional electronic crystals. So on top, you see STM measurements, scanning tunneling microscope measurements in such a two-dimensional electronic crystal. And what you see at the bottom is the emulation of this scanning tunneling microscope process on a quantum annealer. And what one can conclude from this scientific work is that reproducing the dynamics or the time evolution and the temperature dependence of this domain configuration shows that pink noise plays an important role in this dynamics. And this as well in the experiment with the scanning tunneling microscope as in the annealing. So with this, you can see that you have a new approach to studying non-equilibrium quantum any-body dynamics. The goal is, as Thomas already explained, to combine HPC, exascale system with such a quantum annealer. Why? We want to give tasks that a quantum annealer can do better than an exascale system, maybe some optimization, machine learning, to the quantum annealer. And the other thing is, which can be a huge advantage, is that the quantum annealer can do this for us with usage of much less power. That's the huge advantage. So present and near future, as I already mentioned, we purchased the D-Wave Advantage 2 system, and this will allow us to experiment with the system. We can change the parameters, but that's not all. We will also have a very close research collaboration, and with this, we hope that we can come to applications together with D-Wave and their customers on the hybrid, HPC, quantum, and also AI computations for applications. So, and with this, I would like to summarize. So in Jülich, we have this experience with modular computing. So for us, it's very natural to add quantum systems as a module. And as such, we want to combine all these modules to do computation. And computation means what is now called classical simulation, AI, and quantum computing. So therefore, we very much look forward to this coupling of the new D-Wave Advantage system to our exascale system, which will be up and running in summer of this year. And then you will see a complete new way of solving numerical and real-world problems. Thank you very much.